Okie doke, dear students, it's time to talk about a force that we all are very experienced with. Every time we drop an object, we see its effects. That force, of course, is weight. Also, another one with which we are very experienced, but we don't usually think of it very often, is known as the normal force. So, two forces in one lecture. And notice that I've combined here ideas from section 6 and 7 from chapter 5. I find it better to put these two together and then to move forward with them both sort of in our pocket. It's hard to talk about one without the other. So, weight and normal forces are what we're talking about. Now, weight is basically the how do I have it worded here? The gravitational force exerted on an object. So, weight equals the gravitational force exerted on an object by another object. Normally we talk about weight. It's the earth that does the pulling. Force exerted on an object. It's that simple. Now, the definition in your textbook says it's the gravitational force exerted on an object by the Earth. It's true, but your weight, you still have weight on the moon. It's just a different weight. So I'm just going to leave it there. Gravitational force exerted on an object. Let's take a simple case here. Let's figure out what the weight is equal to in terms of things that we already have talked about, quantities that we're already familiar with. How do we express the weight? Well, all you got to do is imagine a ball falling down through the air, or through a vacuum. We're not worried about the air right now. Right? This is a force vector on the ball. This is the weight vector. Somebody's calling me. Who's calling me? My mom is calling me. Sorry, Mom. I'm doing physics. So that is the weight vector pointing straight down. No other force is acting on it, just gravity, right? Just the gravitational force exerted on an object. For example, the baseball. There it is. There's the weight vector, straight down. And I put the bar over the W because it's a vector. Okay? Actually, let's just leave that vector sign off. It's pointed down. It's got a magnitude of W. Okay? So, let's apply Newton's second law to this simple situation. We don't have to worry about doing it in the y direction, right? Because all the motion is in the y direction. All the forces, gravitational forces, are only in the y direction. We spent almost all of chapter 4 talking about this, that gravitational forces operate only in the y direction. So, here it is. Sum of forces in AY, right? We don't have to worry about the x direction. There are no x forces here, so we don't have to do this Newton's second law business. By the way, let me say something. Have you noticed that every time I've come around to a new problem or a new example, I have started with Newton's second law? That's a pattern I want you to notice. Virtually all of the problems in chapters 5 and 6, if you don't know how to start them, I'll tell you how to start them. You start them by applying Newton's second law. That's what you do. You draw a free body diagram, like right here. And then you use Newton's second law. Okay? Notice that. Every example I'm going to be doing. And we got 3 examples coming up after this video. All start with Newton's second law. Okay? They all involve Newton's second law. So, what are all the forces acting here? All the y forces? Well, there's one force, it's weight, and it's down. Up's positive, down's negative, as per usual. So our forces are minus W. That's it. That's it. That equals mass. What's our acceleration? Object falling freely in space. Free fall. What's our acceleration? If up is positive, as it is, acceleration is minus g. So apparently, right, we got a minus sign on the left-hand side, we got a minus sign on the right-hand side, we can get rid of them. So apparently weight is equal to mg, and that is golden. That is the weight of an object. Weight is not the same as mass. Weight is mass times g. And of course the units, good old newtons. It's a force. All forces for us come in units of newtons. So the weight of an object is equal to mg. So if I have a mass of 70 kilograms, which is actually quite high, I think, for me. But let's say I have a mass, 70.0 kilograms. That means my weight is going to be my mass times 9.81 newtons, which comes out to be 687 newtons. Actually, that's closer than, that is pretty close to my weight. 687 newtons, which is about 154 pounds. Okay. That's my weight. It's 687 newtons. That's on Earth. Okay. If I go to the moon, which would be great, so this is weight on Earth, W sub E. If I go to the moon, which would be awesome, I still have the same mass, right? I still have the same amount of quantity of matter. I got the same amount of stuff in me, right? I'm not smaller or bigger. I'm the same person standing on the moon. But the moon's gravity is 1.62 meters per second squared. It is far less than the acceleration on the surface of the Earth. So if you drop something on the moon's surface, it would seem to fall in slow motion. The acceleration is roughly 1/6 that of the Earth. And I would have a weight on the moon of 113 newtons, which is only 25 pounds. So my mass on the moon's the same. Whether I'm on the Earth, on the moon, on the third moon of Jupiter, Callisto, Europa, whatever. Whatever moon I happen to be on, whatever asteroid I happen to be walking around on, my mass is the same. Does not change. My weight, however, does change. Weight depends on how massive the body is I'm stuck to. So a larger body like Jupiter, which you can't actually walk on because it's a big ball of gas, but if I could walk on it, I would weigh about twice as much as I do on Earth. But if I go to a smaller body like Mars or the moon or an asteroid, I'll weigh a lot less. So weight changes as you journey around the solar system, around the universe, but your mass remains the same. Okay? Do not forget that. Okay, that's a little bit about weight. Now something about normal forces. Let's take a simple situation here. Let's take a tabletop and a coffee cup. One of my favorite things in the world. A coffee cup with hot coffee in it. You bet. There's my coffee in there. Okay. Now, what are the forces acting on that coffee cup? One force is always the weight. The weight, as long as you're on the surface of the Earth, which I am drinking my coffee here on the surface of our fair planet, there's always going to be, and this is kind of a free body diagram here, so I got my coffee cup drawn as a dot there in the middle. Remember the free body diagram? Diagram with a dot and all the forces acting on it. So the weight is down. But it's not in free fall, is it? It's not falling like the ball that I just erased. Both of them experience their weight. They have a force of the Earth's gravity pulling them down. They both experience weight, and both vectors are down. But this coffee cup's not going anywhere. Why not? Why is the coffee cup going exactly nowhere? It's because the table, right? The table's in the way. The table is pushing up on it, supporting it. There is a force upward on the coffee cup from the table known as the normal force. Capital N. Normal force. It's a particular kind of contact force. In fact, normal forces and contact forces are not always exactly the same thing, but are very similar. We'll talk more about that later. But for now, just know when that coffee cup is sitting there on the table, it experiences a weight down, it experiences this normal force up. Okay. So we have two forces acting in the y direction. Let's see what happens when we apply Newton's second law. Sum of the forces in the y direction is m times ay. So we look at our free body diagram, right? Our free body diagram, and ask ourselves, what are the forces in the y direction? There are none in the x direction. They're all in the y direction here. We have, so our sum of the forces in the y direction, we have normal that's positive minus mg, the weight, down. Okay. Actually, let me just call that, let me see, what did I do here? Yeah, I just call it the weight. Sometimes I'll write the weight as W, sometimes I'll just write it as mg. Because the weight is always mg. But here I'll just keep it as W. Equals MAY. The mass we don't know. Didn't give it to you. Doesn't matter though, because what's the y acceleration of that coffee cup? That y acceleration is equal to, class, stick with me here, the y acceleration is equal to 0. That coffee cup ain't going nowhere, right? It's not accelerating upward. It's not accelerating downward. Its velocity is 0. Its velocity is constant. When velocity is constant, there is 0 acceleration. So MAY is 0 because A sub y is 0. Any mass times 0 will give you 0. So look, the normal force is equal to the weight. Whatever the weight of the coffee cup is, those two forces are equal and opposite. They cancel out. The net force is 0 because the normal force up has the same magnitude, opposite direction as the weight down. Those two forces act on the same body and completely cancel out. This is not, please listen to me, normal force and the weight does not, that pair does not constitute, not constitute a Newton's third law pair. Why? It does not constitute a Newton's third law pair because both the normal force and the weight act on the same body, the coffee cup. Newton's third law pairs always act on different bodies. Always and forever, amen, world without end. Okay? Both these forces, the normal and the weight, act on the coffee cup. So they happen to cancel out, be equal and opposite. But just because two forces are equal and opposite doesn't mean they're a Newton's third law pair. This one is not because they both act on the same body. Okay? Now, you might be tempted to think that the normal force is always equal to the weight. It is not. The next 3 videos are going to be examples, worked, detailed examples of situations where the normal force is not equal to the weight. It is for this coffee cup in this situation, but in general, the normal force is not equal to the weight. So this is not always true. That's always true. The weight's always mg. This happens to be the case for this coffee cup, but not always. Coming up, 3 different videos, 3 different examples of situations where the normal force and the weight are not equal.